Good morning, everyone. I'm Ruibin. Today, I'm going to present ctFS, a persistent memory file system to replace file indexing with hardware memory translation through a contiguous file layout. This is a collaborative work with my colleagues from the University of Toronto. So, persistent memory is one of the most exciting hardware evolutions in decades. It fundamentally blurs the boundary between main memory and persistent storage. It sits right in the middle of the computer storage pyramid while trying to steal jobs from its neighbors. As a storage device, persistent memory's impressively low latency is shifting the bottleneck from I/O to indexing. As a result, many file systems have been proposed to fit the characteristics of a persistent memory in recent years. However, all of them still treat it as a block-based device and rely on software indexing. For example, ext4 DEX is a port of the ext4 file system in Linux to support direct access to persistent memory, with the only difference being bypassing the file cache. Let's take a brief look at its indexing path. It needs to go through multiple levels of interaction in the extend tree to translate an offset to a logical block number, which is essentially a virtual page number. These are all done in software. Then the memory management unit, which is piece of hardware, further translates the virtual page number to PM physical page frame with direct mapping. The tedious software index translation takes up a huge portion of the total runtime in our macro benchmark. The benchmark consists of 6 tests. In particular, the append test writes 4 kilobytes of data at the end of a file, sequentially write empty, or SWE in short, writes 1 gigabyte each time to an empty file. With a closer look at the ext4 DEX, we find that indexing contributes 45% to the runtime in append workload and 43% in SWE. That's also more than 20% in random read and write workloads. SplitFS tried to reduce the software overhead by leveraging mmap to avoid redundant indexing costs and using staging files to optimize the append workload. Despite all these, the indexing cost still takes a significant portion. In addition to SplitFS, HashFS and Google also study indexing cost and propose new indexing mechanisms, such as replacing the extend tree with a hash table. However, all of the existing proposals still rely on software indexing. Let's take another look at the access path of ext4 DEX. Almost all the proposed solutions are trying to optimize the software side while leaving the hardware doing virtually nothing, as in every logic block is merely mapped directly to a physical page frame. So why not eliminate all the complicated software indexing and start making use of the MMU? After all, persistent memory is still memory, isn't it? In ctFS, we replace software indexing with existing hardware memory translation. This is only possible given that PM is better addressable and MMU managed. We allocate all files and directories contiguously in the virtual address space and only store the starting virtual address in the inode. In this way, every file access is a simple offset calculation in software. The physical data location will be further indexed by the MMU in the CPU. This translation will be managed by the persistent page tables stored in the PM, which share the same structure as the Linux page tables and are copied to DRAM upon page faults. Physical PM pages are not necessarily contiguous, as they are allocated on demand when a virtual page is accessed for the first time. So that's the kernel component of ctFS. It solely provides the memory abstraction to the user level, while the file system functionality is implemented as a library in user mode. Now let's dive into the design details of ctFS user components. Despite the beauty of contiguous allocation, there are 2 major design challenges. One is how files are allocated. Fixed size partition results in severe internal fragmentation, while variable size partition has the problem of external fragmentation and requires expensive garbage collection. We propose a novel hierarchical file system layout to address this challenge. The other challenge is resizing. A file may grow and conflict with another file. In this case, the file needs to be relocated, which sounds like an expensive operation. However, our new system called Pswap can solve it with a negligible cost. ctFS tackles the first challenge with a unique hierarchical file system layout inspired by the body memory allocator. Here is an overview of the layout. We divide the virtual address space into partitions of different levels. Each higher level partition, shown in blue here, subsumes 8 lower level partitions. Each partition in gray is occupied by one file. The size of each partition is 8 times the lower one, starting from L0 with a 4 kilobyte page size. Every partition's starting address is strictly aligned to its size. For example, an L6 partition has a starting address of multiple of 1 gigabyte. Here, we demonstrate a 10-level setup, but it can be extended to support larger PMs. Every file resides in the smallest partition it can fit. For example, a 100 megabyte file is in an L5 partition, and a 200 megabyte file is in an L6 partition. A partition can only be occupied by one file, and once occupied, we say it's in the allocated state. Note that although the remaining portion in the partition is wasted, it's only a waste of virtual addresses. Physical PM pages are not wasted thanks to demand paging. So how are the partitions organized? Let's start with a big L9 partition located in the virtual address space. This L9 partition is divided into 8 L8 partitions. So we say it's in the partitioned state. The second L8 partition is occupied by a file, so it's in the allocated state. The first and third subpartition are in the partition state, which is further divided into 8 L7 partitions, and so on. Each partition in the partitioned state can be divided until L4. The headers at the beginning of every partition in the partitioned state contain the metadata. Each of them is 4 kilobytes in size and is shared among all the lower level partitions. In the header, the state map records the state of each subpartitions, and the availability level tells us the largest subpartition it can accommodate. ctFS does not allow L3 partitions to be further partitioned in the same way because the fake 4 kilobyte header page is getting wasteful. Instead, each L3 partition is divided evenly into lower level partitions. The highest level of the partitions needs to have the size of at least 2 times the PM capacity. From the top view, the virtual address space of ctFS consists of 2 such highest level partitions, one for metadata such as inode table, the other for actual file data as we just described. For instance, a 256 gigabyte PM needs as high as level 9, and then 2 L9 partitions are reserved in the virtual address space. Recall that the second challenge is file resizing when a file grows over its partition size. To solve it, we introduce a new system call Pswap. It atomically swaps the mapping of 2 same-size contiguous sequences of virtual pages. The interface of Pswap is shown here. When a file is expanded beyond the size of its current level, an upgrade is triggered. Assume we want to expand a 100 megabyte file to 200. ctFS will first allocate an empty higher level partition. In this case, it's an L6 partition. Then Pswap is called on the old partition with the new one. Finally, it writes the additional data to the end of the file. Since Pswap may be on the critical path of an append operation, it has to be efficient. So how does Pswap achieve efficiency? The most obvious way is swapping page table entries rather than copying the actual data. But that's not all. Recall that Linux uses multi-level page table, which has 4 levels in the current setup. Each page directory has 512 pointers pointing to the next level directories or page tables. Therefore, each such pointer can represent a large set of data. For example, a PUD pointer can represent 1 gigabyte of data. So in our previous example, Pswapping 128 megabytes now only needs to swap 64 pairs of PMD pointers, rather than more than 32,000 pages. This trick works best when the swapping areas are aligned, which is always the case for ctFS partitions. This log plot shows how fast Pswap can be compared to memcopy on a logarithmic scale. When a number of pages is less than 4, memcopy is slightly faster for the fact that Pswap is a system call. However, at 512 pages, Pswap is already hundreds of times faster. The difference is even amplified to tens of thousands of times when swapping 512 squared pages. In addition to enabling efficient file resizing, the capability of Pswap can also improve the performance of an atomic write. For example, we want to overwrite the blue area in the file at L5. We first allocate a staging partition at the same level as the file. Then write new data to the new partition at a given offset. If the write is not page aligned, we copy the data fragment to the new partition. Lastly, 2 affected areas are Pswapped. We further note that if every write is atomic in a file system, it's in strict mode. Otherwise, it's in sync mode. So given the variety of techniques that ctFS has applied, how does it perform? Let's find it out. We revisit the macro benchmark results. ctFS indeed managed to eliminate the majority indexing cost and achieve 6.7 times speed up over ext4 DEX in the append workload, and 2.1 times over SplitFS. Overall, it's average 117% faster than ext4 DEX and 97% faster than SplitFS in all the other tests. Yahoo Cloud Serving Benchmark, or YCSB, is a real-world database benchmark tool, which includes 6 different key-value workloads. In sync mode, ctFS achieves an average of 64% performance gain against SplitFS and 188% against ext4 DEX. In strict mode, the speed up against SplitFS is 30% on average. As you can see, the elimination of software indexing improved the real-world application performance by a large margin. But outstanding performance, however, does come with a trade-off. Because all metadata operations happen in user mode, the production of ctFS is a weakness. It was designed to maximize performance. To reduce the risk, we used an Intel MPK to prevent memory bugs from corrupting the PM data. Nevertheless, intentional attacks are not prevented. In the next step, we plan on migrating the metadata handling into the kernel. That concludes my presentation. Thank you all for watching, and I'm ready to take questions.